GT McDaniel. I'm a process control supervisor at LAR, Los Angeles Refinery for Marathon. I've been in manufacturing for about 20 years. I've been at Marathon for about 13 years. I started my journey at Marathon as a process chemical engineer. Then I went into controls. I did a couple assignments at various other sites, just temporary assignments, and then worked my way into supervision for process control, and I'm a working supervisor for advanced control APC and major projects. So any major projects associated with automation. So I've always been an early adopter of technology, so it kind of made me fit for the AI role. Our board of directors and leadership said that we wanted to start looking at AI, and I raised my hand and said, absolutely, let's go do this. We looked for opportunities. One of the ones that we found was in our NAPTHA system, and we knew that there was value, so we invited some vendors to come and do a bid process. And after evaluating all the technologies, we then settled on Imubit. Imubit was the only actual controller that was like an AI optimizer that was closed loop in the field. They could write to DMC or write to the controllers. The others that we saw didn't really give us that, and it felt like it was not diving all the way in. So, Peter, do you have the clicker? All right, cool. So a little bit about Marathon. We are, I think, the largest refiner in the United States. They've been around for a very long time, and we're well placed as an industry leader. So leading into AI was something they really wanted to do. They have a lot of strategic partners, and our big general partner, MPLX. You can kind of see the footprint for refining. It's a pretty large footprint across the nation. If you ever get a chance to go to our website, I suggest you pull up the map with MPLX on it as well. It's huge, and it gives you a little bit more view on how big the company is. I work at LAR. This is our West Coast refineries. LA is actually 2 sites put together. We're actually integrating them now. And it's Carson and Wilmington. PCH actually runs right down the middle of it. All right, so I want to jump right into the model itself. This is a naphtha splitter system that has 3 independent towers. Part of the problem we had was they all operate differently. They're not the same style. The feed comes in from a DHEX bottoms and naphtha bottoms, and they're 2 DMC controllers. So the first 2 towers have a DMC controller on them, and the third one does not. So optimizing that system ended up becoming a nonlinear problem. They independently operate fine, but then when you try to optimize to an economic and planning target, the variability is pretty wide. You can kind of see the yields on each tower because they're designed differently in different outputs. If you're trying to target something towards the right-hand side, and I kind of blurred this out, but if you're trying to target something on the right, the third tower doesn't operate that well. If you try to operate on the left, you're missing out on opportunity on the first 2 towers. Another problem we had is that they're 2 operating areas. So communication between the 2 operating groups is tough. You have the crude units on one and then an SFIA group on the other, and they have to be able to communicate and work together to kind of get that last yield. Another problem that they have is that economic and planning target is set as a pool target, a final target. And so they have to manage each tower separately. So they can, run one a lot harder and run one a lot less to get that blended, but it gives you a lot of variability. So there's a lot of opportunity here. So we chose the AIO option. So why Imubit? They were the nonlinear solution that we needed. We had a nonlinear problem. You can solve each individual tower with an APC controller, right? That was fine. But once you started to look at the entire problem and then the pool, you really needed something that could handle more. So it also works with DCS and DMC. You can write to both. And it ended up becoming a common platform where the two operators could communicate through. They both had the same interface. They can chat through it and they can talk through it too. So the model itself, kind of digital twin, it's not a simulation environment. It's not like you're building a tower and heat exchangers and pumps. We took a data-driven approach, and it's really data that you're looking at. You're looking at trends, you're looking at some special visualizations to look for opportunities and alignments, and where you're not aligning as well is important. So you end up building inferentials and like a virtual simulation of these plants. It's the deep learning predictor. And then you jump into the reinforcement model is where the AI comes in, is after you've kind of worked and build that supervised kind of training of getting your data scrubbed with your process engineers. Then you throw it into the DLC and it gives you their deep learning controller, and it will build out 10,000 iterations over your data. So we had no data quality problems. We have decades of process historian data that was acceptable for the model. So we chose the right parameters. We knew what we were trying to do in that naphtha system. You built out the inferentials, you built out the simulation, and then you build your reinforcement learning model. After you build that model, then you have a toy you get to play with. It's got predictions. You can say what happens here, and you can watch what it does. You can see what it's going to be doing for your system. Then you can actually see where, like, it's a distribution curve, and you can kind of see where that distribution curve lies in relationship to other parameters. If you're familiar with DMC, where you have your curves, it's very similar to that in your matrix, but it's every iteration lines up with itself, so then you can get that non-linearities in a visual format. So once you're satisfied with the model and you have it ready to go, you turn it into an offline optimizer, and it becomes a controller that sits at the DCS level or right at above the DMC level, and can write to the DCS and optimize for our solutions. So what we ended up doing was 6 MVs. It's a fairly large model. Lost my thing here. It is feed and reflux. We ended up having 3 objectives. We wanted to maximize the total naphtha. We wanted to minimize the bypass around this system. And we wanted to meet that economic target, reduce the variability. As a kind of a bonus there, if we're meeting those criteria, it also minimizes the steam output. So we're trying to save on energy. And so part of what we've been seeing after the last couple months is we're actually seeing exactly that. So the model does what we need it to do. We've made a couple adjustments to it here and there. We're actually starting to look at where the bottlenecks are in the field. So valve trims that we need to adjust. The reboilers are fouling at different rates, and how it can justify going and doing a reboiler cleaning now because of the value generation. And so we can actually visualize the benefit, whereas with some traditional APC models, we have rules of thumb or we have benefit analyses that aren't actually visualized. And so the result here is, our teams have collaborated a lot more. You've got the 2 units that have a common interface. We actually are getting the yields over time based off of baseline. So we actually have increased throughput. We actually have better yield. We actually have steam reduction. Well, that's about it, guys. That was my presentation.